Lesson 54 teaches us about velocity and acceleration and motion due to gravity. We start off by talking about the position function, and the position function states the position of an object, usually along a line or a number line, in terms of time. So here's just a quick example. Let x of t equal 2t be a position function. So if we put 3 seconds in there, the position would be 6. The slope of the position function, so we're looking at this next part now, is in units per second. So the derivative of the position function is velocity. So when we know that when we take the derivative of something, that is a rate, and the rate in this case is units per second, and we know that measures velocity. And then taking that a step further, taking the derivative of the velocity function, which happens to be the second derivative of the position function, will give us the acceleration, because that's the rate at which the velocity is changing. So in this case, when the position function, it was just 2t, its slope was the velocity, and then the slope of the velocity is the acceleration. Well, if you look at the slope of this velocity function, sorry about that. If you look at the slope of that, of this function, it's just 0, so the acceleration is 0. So it's not speeding up or slowing down. So we're going to look at a few different examples with this. The position of a particle moving along the x-axis at any time t in seconds is given by this equation. X of t equals negative 3t squared plus 4t plus 2. Find the position, velocity, and acceleration of the particle when t equals 3. Well, to find the position when t equals 3, all we're doing is plugging in 3 into the position function. So this is going to be x of 3, which is negative 3 times, so we're using this function right here, 3 squared plus 4 times 3 plus 2. 3 squared is 9 times negative 3 is negative 27, plus 12 plus 2, and that's negative 27 plus 14 is negative 13. So the position is at negative 13 on the x-axis. Next, we want to find velocity. Well, we know velocity, from what we just talked about, is the derivative of the position function. So velocity, which I'm going to put equals the derivative of the position, is equal to negative 6. So again, we're going to find the derivative of that, negative 6t plus 4. And we want to find the velocity when t is 3, so we just plug in 3. So v of 3 is the same thing as x prime of 3. And you don't have to write both of these things. I'm just trying to remind you. So negative 18 plus 4 is negative 14, and this is units per second. Well, a negative velocity means it's moving in the negative direction. It's moving to the left. And then acceleration. Acceleration, we know, is the derivative of the velocity function. This should be a t. A of t is v prime of t, which is the second derivative. So we'll come up here to our velocity function. We'll take the derivative of that, which is negative 6. That's it. So acceleration at 3 is negative 6, and this is units per second squared. And yes, at 3, it's negative 6 units per second squared, but it's always negative 6 units per second squared. So that's the acceleration function for this specific situation. Okay. We're going to talk about a few things here. So when you read through problems or think through some problems, you know what it's asking about or talking about. So it says find the position of a particle moving along the x-axis at any time t is given by the equation x of t equals t squared minus 3t plus 2. Find the times when the particle is momentarily at rest, the times when the particle is moving to the right, the times when the particle is moving to the left, and find the times when the particle is decelerating or accelerating. So decelerating is when the acceleration is negative. Acceleration is when it's positive. So we need to be able to translate these phrases and what they mean in terms of position, velocity, or acceleration. So momentarily at rest, if something's at rest, it's not moving, it does not have a velocity. So we want to know when the velocity equals 0, or in this case, the first derivative. So we could take x prime of t. So we're going to take the derivative, which is 2t minus 3. And we want to find when that's equal to 0. So 0 equals 2t minus 3. And we could add 3 and divide by 2. Oops. Add 3, divide by 2, and we get t equals 2/3. That is when this is momentarily at rest, which we'll talk about that again in a few minutes. So moving to the right. Well, moving to the right means the velocity is positive, or the first derivative is positive. So we want the first derivative, which we found here, 2t minus 3, to be greater than 0. Add 3, divide by 2. We're not dividing by negative, so it's moving to the right when t is greater than 2/3 seconds. So we're going to assume this isn't seconds. We talked about that earlier, I think. So after 2/3 seconds, it's moving to the right, and it's always moving to the right after that. When's it moving to the left? Well, it's moving to the left when the velocity is negative. So we would want when the velocity, which is 2t minus 3, is less than 0. Add 3, divide by 2. So when t is less than 2/3 seconds, it is moving to the left. Acceleration. Acceleration is the second derivative. So this, I should have written this up here. Our velocity function is the first derivative. Our acceleration function is the derivative of velocity, or we can think of it as the second derivative of position. And so we're going to take, here's the velocity function, acceleration, or the derivative is just 2. And it's always 2. Which means it's always accelerating. So accelerating, so always accelerating. Now we have to be careful about what acceleration means. It's never decelerating. Acceleration is a vector. The idea of a vector quantity, which means direction is important. So here's the situation here. It says it's moving along the x-axis. So here's an x-axis. And let's say this is 0, and then we have positions along this x-axis. All right. At 2/3, well, let's say we start at 0 seconds when time is less than 2/3. Before I get into this, so we have answered all these questions. I just want to explain what this looks like in the actually what we're talking about if a particle is moving. But so if t is less than 2/3 seconds, so really if we're talking about initial time less than 2/3, it's moving to the left. So it's moving to the left. Then at time 0, it is momentarily at rest. So that means it's moving to the left, it's slowing down, and then it stops at 2/3 seconds, and then it starts moving to the right. moving to the right. So acceleration means it's tending, it could be slowing down to the left, or it could be speeding up to the right. So we have those different answers that we were looking for. It's always accelerating, and those are some of the relationships you'll need to know as you work through acceleration, velocity, and position. All right, now we're going to look at, instead of moving on a number line, the x-axis, we're going to talk about acceleration due to gravity. So in physics, an object moving upward has a positive velocity and acceleration, and moving downward has a negative velocity. And it's the same for acceleration, which I just mentioned. Therefore, acceleration due to gravity is negative. It's pulling an object towards the earth. So moving up is a positive velocity, and this velocity is a vector quantity, so direction matters. The fact that it's moving up is positive and down is negative. So a ball is thrown vertically into the air. So its height in meters at any time t is given by this height equation, negative 4.9 t squared plus 20t plus 2. Find the height of the ball and the velocity of the ball when t equals 1. Well, to find the height of the ball, you just plug it into the height function. So h of 1 is going to be negative 4.9 times 1 squared plus 20 times 1 plus 2. Well, this is going to be negative 4.9 plus 22. So this is going to be 17.1. Uh, 17.1 meters. Because it says meters right here. And we also want to find the velocity. Well, the velocity is going to be the derivative of the height function. So velocity is going to equal h of t. And then what we want to do is we're going to take the derivative of this. The derivative is, so the derivative of this function here, negative 9.8 t plus 20. And we can find the velocity when t is 1 by plugging in 1. So v of 1 is negative 9.8 times 1 plus 20. Well, that's negative 9.8 plus 20, which is 10.2. And this is going to be in meters per second. So after 1 second, it is 10.2 meters per second, and it's a positive, which means it's still moving upward. So you got to know these important things about direction and positives and negatives. At what time is the ball the greatest distance above the ground? Well, we have to think through this just a quick second. When it's the greatest distance above the ground, so it's going, the ball goes up, and then it comes down, right? So that's its greatest distance, and that is when it is momentarily at rest. It's going up, gravity's pulling it down, it comes to a stop. So velocity is 0. And so what we want to do is we want to find when the velocity is equal to 0. So we have negative 9.8 t plus 20 is equal to 0. We could subtract 20 from both sides. So negative 9.8 t equals negative 20. And we can divide both sides by negative 9.8. Dividing both sides by negative 9.8 gives us 2.0408. 2.0408. That was from dividing both sides by negative 9.8. So when the time is 2.040 seconds, is the time when it's its greatest distance above the ground. Well, it says how high does the ball go? Well, we want to plug that time into our height function. So we're going to take our height function, which was our original function given, and we're going to plug that value in there, so 2.0408. And so you can plug that in, negative 9.8 times 2.0408 squared plus 20 times 2.0408 plus 2. You can square those things. You could probably put the thing right into a calculator, and you get 22.4082 meters. So what we did is we found the time when it would be the highest, because we knew that's when the velocity was equal to 0, because the ball went up, came to a stop, and then came back down. Then we plugged that time into the height function. What is the greatest value of acceleration? Well, acceleration is the derivative of velocity. So we come up, here's our velocity function. We want to take the derivative of that, which is negative 9.8. And it's always negative 9.8. So this is negative 9.8 meters per second squared. The greatest value of the acceleration, well, it's always the same. So the greatest is negative 9.8 meters per second squared, which is really important because that actually is a very important value in physics. That is acceleration due to gravity here on Earth. If you go to other places like the moon or another planet, velocity or acceleration would be different. So there you have it. The relationship between velocity, position, and acceleration.